In this series of electrostatics where we find electric field due to continuous field distribution, we are going to calculate electric field at a point x away from a ring of radius r having charge q. So consider a ring of radius r having charge q uniformly distributed all over it, and we are interested to find electric field at this point situated at a distance x away from the center of the ring. Now we have followed a simple process for such continuous charge distribution. The first step here is to select a tiny element, then find the electric field only due to that tiny element, and in the final step we integrate for the whole body. Now to follow those three steps mathematically, first we select a tiny element. This teeny tiny element over here has charge dq over it. It is situated at a distance square root of x square plus r square from our point of interest. Since here we have the right angle, it makes an angle theta with x. Electric field due to dq at this point is pointing along this direction that will have magnitude dE. Now dE will have components dEx and dEy. All the components of dEy, if you take all the elements along the circumference of the ring, then these vertical components will cancel out each other, and therefore the final electric field will only be due to the x components. Now since this is theta, this angle will also be theta. Therefore dEx will be equals to dE cos theta. Now dE is nothing but k dq upon square root of x square plus r square the whole square into cos theta. This square root and this square will cancel out each other. Therefore you have k dq upon x square plus r square into cos theta. Now from the triangle we can find the value of cos theta, that will be adjacent upon hypotenuse. Substituting this value over here, we get dEx equals to k dq upon x square plus r square into x upon square root of x square plus r square. Now this is the electric field due to this tiny element having charge dq. Therefore to find the electric field due to the entire ring, we need to integrate. So integration of dEx will give you the value of final E, that will be equals to integration of kx dq upon x square plus r square raised to 3 by 2. Now here the distance between the center of the ring and the point of interest is constant. Radius of the ring is constant, k is constant. So the only thing you will integrate is dq, and obviously the integration of dq is nothing but q. So your final expression will be E equals to kx q the whole upon x square plus r square raised to 3 by 2. This derived expression is correct if we can simplify it for a point charge. So we assume that r is nearly equals to 0. Therefore substituting this in the above relation, we get E equals to kx q upon x square raised to 3 by 2. Simplifying that, we get E equals to kq by x square. Since we were able to simplify the expression for ring to a point charge which comes into our original format kq by distance square, it means that our expression for the ring is correct. Can you tell me what will be the electric field at the center of the ring? Leave your answers in the comments or on my Facebook page, Physics Tutorials.